Hello and welcome to today's class. My name is Dr. Wenjara Titus. Today I will be taking you through the moment generating function of a binomial distribution. As well, we are going to derive this moment generating function of a binomial distribution. Thereafter, we shall be able to determine the mean and variance of a binomial distribution using the moment generating function. And therefore, let us straight away start by looking at the moment generating function of a binomial distribution. We all know that the moment generating function of any variable is given by the expected value of x exponential tx. But since a binomial distribution is discrete, then we say the moment generating function will be the summation of x, or all possible values of x running from 0 all the way to n. We have exponential tx f of x. But we know the probability mass function of a binomial distribution is always given by the probability mass function of a binomial distribution is given by n combination x, probability of success, probability of failure, which is n minus q x. Are we getting it? Then now we have to derive the moment generating function from this general equation. Then we'll say the moment generating function is going to be the summation of x, or all the possible values from x heading to 0 all the way to n, exponential tx. Then we have to add the probability mass function of a binomial distribution, which is n combination x, probability of success, probability of failure. Yeah. But let us look at this. We have those powers raised to x, meaning we can put them together. So we shall have the summation as x heads to 0 all the way to n. Then we have n combination x. Then we say it will be p exponent t all in one bracket raised to power x. Are we getting it? Then we have q n minus x. But we know the value of x, or the possible values of x, are running from 0, 1, 2, 3 all the way to n. Then it means we are going to replace the values of x in the above equation. Then we will say the summation as x heads to 0 all the way to n, we are going to have n combination x, probability of success exponent t all in x, q n minus x. Then this one is going to be n combination 0. We start from 0 all the way to n. Then we have probability or exponent t raised to 0, q n minus 0. Then we add n combination 1. Then we have probability of success exponent t. We have to add 1 q n minus 1. We have to add plus, it will be n combination 2, probability of success. We have these 2, q n minus 2, then all the way to n combination n, all the way to n, probability of success. Then we add raised to n, then we have q n minus n. Are we getting it? Then in reaching there, all these under the binomial theorem, this one can be replaced by, or our moment generating function will be q plus the probability of success raised to t raised to power n. All of this one is replaced by this one. So our moment generating function of a binomial distribution is given by this one. Are we there? So we have now to check on how we can now derive the mean from this moment generating function, mean. So we all know the expected value of x, or the mean, is always given by the summation of x, f of x, under the normal distribution, binomial distribution. But here we are going to use the moment generating function. So once we are going to use the moment generating function, we are going to find the first derivatives of the moment generating function. First derivative of the moment generating function with respect to t heading to 0. Then our moment generating function is given by q plus p exponent t all to n. So we are going to find the derivative of the first moment generating function. So this one is going to be, when we differentiate this one, is going to be n into what is in bracket here, which is q plus p exponent t. Then we have to multiply by this derivatives of what is in bracket here. When we differentiate this one, it's going to be 0 plus. When we differentiate this one, it's going to be exponent t. It's just going to remain the same. Are we getting it? But all these with respect to t heading to 0. Then at the end, we will have n into q plus p exponent t. We have p exponent t. But all these t heading to 0. Yeah. So when we replace the value of t with 0, we will have n into q plus p. Because any number raised to 0, it will be 1. Then here it's going to be p. So, but remember, q plus p is always equals to 1. Then it means our expected value of x is going to be np, because it's multiplied by 1. So expected value of x is going to be np. Is it okay? Let us now find out the derivatives of finding the variance. But we all know variance is equals to the expected value of x minus the expected value of x all squared. But now we have to differentiate the expected value of x squared is equals to the second derivatives of the moment generating function with t heading to 0. Now, let us now differentiate or find out the second derivative of the moment generating function. Since the first derivative of the moment generating function, we got it to be that was n into q plus p exponent t, p exponent t. That was our first derivative. So we are going to use the broad product rule. Under the product rule, this was supposed to be n minus 1. N minus 1. Yeah, it was to be that way. So when we use the product rule, we are going to have n into n minus 1. Then we have q plus p exponent t, n minus 2. Then we have to multiply by this one, which is p exponent t. We add the value of u and deviant, all that, which is going to be n into q plus p exponent t with this one. With this one, we repeat the same, which is p exponent t, t heading to 0. So what are we going to do? What we are going to do is to replace the value of t with 0. So when we replace the value of t with 0, we are going to have n into n minus 1. This one is going to be q plus p n minus 2 p, because this one is just 1, multiply by this is going to be p multiply by p plus n into q plus p, that is going to be p. Then at the end, this one is going to be defined as n into n minus 1 p squared plus this np. This one is just np. Then what we are going to do is now to finalize on this, whereby we are going to have n squared minus n p squared plus np. So this one will remain as this one will be what? This is going to be n squared p squared plus n squared p squared minus n p squared plus np. But we all know the variance is equals to the expected value of x squared minus the expected value of x squared. So this one is going to be n squared p squared minus np squared plus np. We have minus mean squared p squared. Then this one will cancel this one. We remain with negative n p squared plus np. So in reaching there, we will have, when we say np minus np squared, so this one is going to be np into 1 minus p. So our variance x, our variance of x is going to be np into 1 minus p, or npq. Thank you for watching, and bye bye. Remember to subscribe in my channel for more information.